All right, today we're going to crack A-level trigonometry problems. You know, the kind that look totally impossible when you first see them. But what if I told you they're just really clever puzzles, just waiting for you to find the key? Let's get into it. Okay, let's just dive right in by looking at a classic exam question. Yeah, it seems pretty intimidating, right? You've got fractions, different trig functions. It's a mess. But I promise you, there is a super clear, simple path right through the middle of it, and we're going to walk it together. So here's our game plan for cracking this code. First, we'll get a handle on the challenge itself. Then we'll build our essential toolkit. After that, it's all about decoding the clues the examiner leaves us, solving the main puzzle, and then, the best part, recognizing the master pattern so you can solve pretty much any problem they throw at you. Okay, first up, the challenge. You see, these A-level questions aren't really about making you memorize dozens and dozens of formulas. No, they're specifically designed to test something else. Can you see the underlying structure of a problem and, simplify it? So to find that structure, you need the right tools. I mean, before you can decode anything, you've got to have the keys, right? Well, the great news is that for the vast majority of these problems, you really only need two essential identities in your entire toolkit. And here they are. Seriously, just these two. And what's so incredible is that these two simple tools, the quotient and the Pythagorean identities, they're basically the master keys. Almost every single algebraic trig problem you're going to face can be unlocked using one, or more often than not, both of them. All right, let's move on to our first puzzle and see how this actually works. This is where we learn to spot the huge clue that the examiner almost always gives you right there in the question. So notice the structure here. Part A asks us to show that this really complicated equation can be rewritten into a much simpler one. Now, this isn't just some random task. It's a massive hint that tells you exactly how you should approach Part B. So where do we even begin? Well, we pull out our first tool. The second you see a tangent x, your brain should just scream, replace it with sine x divided by cos x. This is such a crucial first step, getting everything into the common language of sine and cosine. Okay, now we've got a fraction in the middle of all this, and fractions are just messy, right? So the easiest way to simplify this is to just multiply the entire equation by cos x. That clears out the denominator and gets us one step closer to our target. We are so close now. We have sines and cosines. But remember what our target looks like? It only has cosines. So what do? We pull out our second tool. We see a sine squared x, and we immediately replace it with 1 minus cosine squared x from our Pythagorean identity. And just like that, everything is in terms of cosine. And boom, with one simple bit of rearranging, we've nailed it. We've hit our target. 6 cos squared x minus cos x minus 1 equals 0. We just followed the breadcrumbs and turned this chaotic-looking thing into a nice, clean, simple quadratic. So here's the crucial point. By decoding that first part, we've transformed a really difficult trig problem into a familiar quadratic equation. Now we're on home turf. We know how to do this. Now, part B of the question starts with that magic word, hence. This is another key word from the examiner. Whenever you see it, it means use the thing you just did. They're practically yelling at you. Don't you dare start over with that original messy equation. Solve the simple quadratic you just proved. So now we solve this just like any other quadratic. And here's a great little mental trick. Just for a second, pretend cos x is a single variable, like y or something. That makes it super easy to see how to factor it into two brackets, just like you would in normal algebra. And you know the drill from here, right? If the product of two things is 0, then one of them has to be 0. This gives us two much simpler trig equations to solve. Either cos x equals a half or cos x equals negative a third. From here, it's just a little bit of calculator work for the inverse cosine, and keeping in mind our range of 0 to 180 degrees, we get our two final answers. I mean, look at that. We took that super intimidating expression from the start and just systematically decoded it. Puzzle cracked. Now, I know what you might be thinking. Okay, that was a neat trick, but that was just one specific problem. But here's the amazing thing. It is not a trick. It's a fundamental pattern. This strategy of finding a hidden quadratic equation shows up everywhere in these A-level exams. I mean, just look at these two other examples. The one on the left, it's a quadratic right from the start, just with tan x. And on the right, the examiner literally tells you to create a quadratic in sine theta. Once you see this pattern, you can't unsee it. It's everywhere. So if you only take one thing away from the algebra part of this, let it be this. train your brain to always be on the lookout for the hidden quadratic. Your goal, almost every time, is to use those two core identities to simplify everything down into that familiar form. And this whole code cracking mindset, it's not just for algebra. The exact same approach, identifying the core parts and decoding a puzzle, applies to the visual problems with graphs too. Let me show you how. Here's a typical graph question. We're given a function and we're asked to state its range. This is just another code, but instead of identities, our tools this time are transformations. We just need to decode what's been done to the basic cos graph. Okay, let's break it down. We always start with the core component, the basic cos 2x function. We know that just bounces back and forth between -1 and 1. Simple. Now we decode the transformations. First, it's stretched vertically by a factor of 3/2. So that -1, 1 range becomes -1.5, 1.5. Then, the whole graph gets shifted up by 1/2. So we add 0.5 to both ends and we get our final range, -1 to 2. See? We're just decoding the steps. So, whether it's a messy algebraic equation or a graphical transformation, the strategy is exactly the same. You identify the core components, your basic identities or your basic function, and then you just decode the puzzle step by step using the tools you have. You see, the real key isn't memorization, it's a mindset. Now you have the framework to approach these questions not with fear, but with confidence, like you're a code breaker. So, what problem are you going to decode next? Why not grab one from the source material and give it a shot right now?